Hello, this is video number 12 on my single variable calculus 2. In this video, we're going to talk about L'Hopital's rule. So what is L'Hopital's rule and how do we use it? If you have a ratio and you're trying to find the limit and numerator and denominator are both going to 0 or both going to infinity, then we can apply L'Hopital's rule by differentiating the numerator and the denominator separately and taking the limit of that. We'll go over several examples on that, and then I'll show you a table with all these different forms that are called indeterminate form. So if you look at the first example, we want to find the limit of x minus 1 over cosine of x times pi over 2. So let's plug in 1 and see what we get. So the form of this is 1 minus 1 over cosine of pi over 2. 1 minus 1 is of course 0, cosine of pi over 2 is also 0. So this is of the form 0 over 0. So we have to apply L'Hopital's rule. And if we apply L'Hopital's rule, we're going to get limit as x goes to 1, that was given, and then we have to differentiate the numerator and the denominator. So derivative of x minus 1 is 1, derivative of cosine is negative sine, and then we have to apply the chain rule, so multiplied by pi over 2. Now we can plug in 1, so we get 1 over minus sine of pi over 2, and then we can put the 2 on top, and pi at the bottom, so the answer would be negative 2 over pi. Okay, so let's look at the second example. So in this example, x approaches infinity. What is e to the power of infinity? Well, e to the power of infinity is infinity. What is x squared minus 1? Well, x squared minus 1 approaches infinity as well. So this is the form. So then we can apply L'Hopital's rule. So that gives us the limit as x goes to infinity, e to the power of x is e to the power of x, x squared minus 1 is 2x. Now, if we look at this one, the form of this one again becomes infinity over infinity. As x approaches infinity, e to the x approaches infinity, 2x also approaches infinity. So we can apply L'Hopital's rule again. And let's see what we get. We get the limit as x approaches infinity, e to the power of x over 2. Now, when x approaches infinity, e to the power of x approaches infinity. So the answer to this one would be infinity. Let's look at the third example. So if we plug in 0 in the numerator, we get 0 cubed. In the denominator, we get sine of 0 minus 0. So the form would be 0 cubed over sine of 0 minus 0. 0 cubed is 0, sine of 0 minus 0 is also 0. So then we can apply L'Hopital's rule. So let's see what happens if we differentiate the numerator and differentiate the denominator. Numerator was x cubed. When we differentiate, we get 3x squared. Denominator was sine x, which becomes cosine of x, minus x, which becomes 1. Now, what is the form of this one? As x approaches 0, numerator becomes 0. Denominator is cosine of 0, which is 1 minus 1. So that's also 0 over 0. So again, we can apply L'Hopital's rule again. So that gives us the limit as x approaches 0. Derivative of numerator is 6x. Derivative of denominator is minus sine of x. Now, what's the form of this one now? Again, it is 0 over 0 because sine of 0 is 0. 6 times 0 is also 0. So that means we can again apply L'Hopital's rule. So that gives us the limit as x approaches 0. Derivative of 6x is 6. 6. Derivative of denominator is negative cosine of x. We're going to plug in 0. We get negative cosine of 0 at the bottom. 6 on top. So the answer is negative 6. Let's look at another example. In this example, we have a product. So if x approaches 0, we will get 0 for x. And when x approaches 0, natural log approaches negative infinity. So that comes from the graph of natural log. So natural log looks like this. It goes through 1 comma 0. As x approaches 0 from the right, natural log approaches negative infinity. So 0 times negative infinity is also another indeterminate form because it really depends on how small this is and how large it is. So if you multiply a small number and a large number, on balance, it could be basically anything. It could be infinity, it could be 0, it could be a positive number, it could be a negative number. It could be really anything. So the idea for this one is to put one of these two at the bottom. So either we put negative infinity at the bottom, so turn it into 0 over 1 over negative infinity, which gives us 0 over 0, or we put negative infinity over 1 over 0, which is basically negative infinity over infinity. So either of these two can be done. Sometimes one works better than the other. Let's try and put the negative infinity at the bottom and see what happens. So we take x natural log of x and we put natural log of x at the bottom. So we get this. Now it becomes the form is 0 over 0. So now we can apply L'Hopital's rule. So apply L'Hopital's rule. We get limit as x approaches 0 from the right. On top we get 1. Now the denominator is natural log of x to the power of negative 1. So taking the derivative of that gives us negative natural log of x to the power of negative 2 times 1 over x. So we can simplify this. X approaches 0 from the right. We get x on top, and we get natural log of x to the power of negative 2. And there's a negative sign as well. Now, if I let x approach 0, I would get 0 on top, and I would get natural log of 0, which is negative infinity again. But when you raise it to a negative exponent, you get 0 over 0. So we can apply L'Hopital's rule again. So if I apply L'Hopital's rule, I would get limit as x approaches 0 from the right. I would get 1 on top, or rather negative 1 on top, negative 3 natural log of x to the power of, or rather negative 2 natural log of x to the power of negative 3 times 1 over x. I'm using the chain rule. So let's put the x on top. The two negative signs cancel. We get x over natural log of x to the power of negative 3. So let's look at what happened. We started with x over natural log. We got to x over natural log to the power of negative 2. And we got to x over natural log to the power of negative 3. So things are getting worse, not better. So this doesn't seem to work. So this is not working. So perhaps we need to try something else. Perhaps we can take natural log and keep it on top and put x at the bottom. If we do that, then the form is going to be negative infinity on top, positive infinity at the bottom. So because of that, we can apply L'Hopital's rule. So that gives us the limit as x approaches 0 from the right. On top, we get 1 over x. The bottom is x to the power of negative 1. We can differentiate. We get negative x to the power of negative 2. So that gives us the limit as x approaches 0 from the right. Now, the numerator is x to the power of negative 1. The denominator is negative x to the power of negative 2. So we can use laws of exponents to get x to the power of 1, because it's negative 1 minus minus 2 as x approaches 0 from the right, which means the answer is in fact 0. So we using this method was a lot easier than the other method. The other method actually did not work. So let's try the next one. This is something similar. So it's x e to the power of x, e to the power of 1 over x, and x approaches 0 from the right. So now what is the form of this? Well, the form x is approaching 0. 1 over x approaches positive infinity because the x approaches 0 from the right. So 1 over x approaches positive infinity. And e to the positive infinity is positive infinity. So we can put one of them at the bottom and then use L'Hopital's rule. So let's put maybe x at the bottom. You can try really either one of them and see which one works, which one doesn't work. Sometimes both work, sometimes one works better than the other, and sometimes one of them doesn't really work. So we get 1 over e to the power over x over 1 over x. So this is infinity over infinity. So the form is infinity over infinity. So we're going to apply L'Hopital's rule. So we get the limit as x approaches 0 from the right. We have e to the power of 1 over x. And then we have the derivative of 1 over x. Derivative of 1 over x is negative x to the power of negative 2. Because 1 over x is x to the power of negative 1. And same thing for the bottom, negative x to the power of negative 2. So these two cancel. We get the limit as x approaches 0 from the right, e to the power of 1 over x. When x approaches 0 from the right, 1 over x approaches infinity. E to the power of infinity is infinity. So this time the answer is infinity. So we see these are indeterminate form, meaning that the answers are kind of unpredictable. This answer was infinity. The other answer was 0. We had answers -6, infinity, -2 over pi. So these are completely random. We can't really predict what happens from the beginning. We have to apply L'Hopital's rule. Okay, let's look at another example. So this example, what is the form again? So the form is sine of 0, which is 0, and the exponent is also 0. So this one is a new indeterminate form. So it's 0 to the power of 0. Because it is exponential, we are going to take natural log so that it becomes 0 natural log of 0, so that it is 0 times negative infinity. So we are going to take the exponential, take natural log, turn it into a product, and then use L'Hopital's rule by putting one of them at the bottom. So we are going to evaluate the limit as x approaches 0 from the right of natural log of sine of x to the power of x. When we take natural log, we're going to have to put the exponent to the front. So that was one of the rules of natural log. And when we do so, the form becomes 0 times infinity, or rather negative infinity. So because of that, so let me write down the form. Form is 0 times negative infinity. So we can apply L'Hopital's rule to this one now. So now based on the example that we did, we know that if we put the natural log at the bottom, it's probably going to get a mess. It's going to get a little bit of a mess. So we're going to put the x at the bottom. So we're going to get limit as x approaches 0 from the right, natural log of sine of x over 1 over x. Now, what is the form of this one? Numerator is negative infinity, natural log of 0. Denominator is positive infinity. So we can apply L'Hopital's rule now. So this is the limit as x approaches 0 from the right. Now the denominator is x to the power of -1. So this becomes negative x to the power of -2 when we differentiate. Numerator is 1 over sine of x times the derivative of inside, which is cosine of x. Now we can simplify this limit as x goes to 0 from the right. Well, we can put the x to the power of -2 on top, so we get x squared cosine of x, and we can put sine of x at the bottom. And there's a negative sign, I'll put it right there. Now let's see what form it is. This is the form of 0 over 0 again. So it is another indeterminate form. Previously it was infinity over infinity, now it turned into 0 over 0. But again, we can apply L'Hopital's rule. So let's apply that to see what we get. So this is the limit as x goes to 0 from the right. Denominator is cosine of x. Numerator will have to use product rule. So -2x cosine of x minus x squared times negative sine of x. Let's plug in 0. On top we get 0. At the bottom we get cosine of 0, which is 1. So the answer is 0. Let's summarize what we did. So what we did was we showed that the limit of natural log of sine of x to the x is 0 as x approaches 0 from the right. So if natural log of something is 0, then that thing inside would have to be e to the power of 0. So that means the limit as x approaches 0 from the right of sine of x to the power of x is e to the 0. So the answer is in fact 1. Because we took natural log at the beginning, we'll have to now take the exponentiation. We have to do e to the power of whatever result that we got. So let's look at another example. So this one is the limit 1 plus 2 over x raised to the power of x, and x approaches infinity. Okay, so let's see what happens. If we plug in infinity, let's see what the form is. Well, the base is 1 plus 0, and the exponent is infinity. So that's 1 to the infinity. So because again, it's one of the exponential indeterminate forms, we'll have to take natural log and then apply L'Hopital's rule. So we'll take the natural log. So limit as x goes to infinity, natural log of 1 plus 2 over x to the power of x. So this is the limit as x approaches infinity, x natural log of 1 plus 2 over x. The form is infinity times 0 because natural log of 1 plus 0 is 0. So now we're going to have to put one of them at the bottom. So we will do so with x because putting the natural log at the bottom is not very wise. So we'll do that. Now we will apply L'Hopital's rule. So let's check the form and then we'll apply L'Hopital's rule. So the form is 0 over 0 now. So we will apply L'Hopital's rule. So if we do so, we are going to get the limit as x goes to infinity. We're going to take the derivative of numerator, so it's 1 over 1 plus 2 over x times the derivative of inside, which is 2 times negative x to the power of negative 2, and then divided by negative x to the power of negative 2. So the negative sign cancels, and this one also cancels. Now, as x goes to infinity, we get this guy approaches 0, and then we have a 2, so the answer becomes 2. Now remember that we took the natural log, so what we did was we showed that the limit as x goes to infinity of natural log of 1 plus 2 over x to the power of x is 2. So that tells us the limit of the inside of natural log would have to be e to the power of 2. So the limit as x goes to infinity of 1 plus 2 over x to the power of x is e squared. So that is our answer. Okay, so let's do a few more examples. The first example is when you let x go to pi over 2. So you can try the unit circle, or you can try the graphs of these functions, whichever you're more comfortable with. We are in the first quadrant, so tangent is positive, secant is also positive. Well, when we approach pi over 2 from the left, from smaller values of pi over 2, then tangent goes to positive infinity. So the form is positive infinity minus secant also approaches positive infinity because tangent is sine over cosine. Both of them are positive, and the denominator of cosine is approaching 0. Secant is 1 over cosine, and cosine also approaches 0. So this is infinity minus infinity. That is also one of the indeterminate forms. So the way to handle indeterminate forms of the form infinity minus infinity is to do algebraic manipulations. So let's try that. So let's write down everything in terms of sine and cosine. So tangent is sine of x over cosine of x, and secant is 1 over cosine of x. So this would be limit as x approaches pi over 2 from the left, sine of x minus 1 over cosine of x. So now what is the form of this one when we plug in pi over 2? Sine of pi over 2 is 1 minus 1 divided by cosine of pi over 2. So that is 0 over 0. So we can apply L'Hopital's rule. So we're going to take the limit x approaches pi over 2 from the left. Numerator becomes cosine of x. Denominator becomes negative sine of x. So that is by differentiating the numerator and differentiating the denominator. Okay, so now what do we get here when we plug in pi over 2? Cosine of pi over 2 is 0 and sine of pi over 2 is 1. So the answer is then 0. Okay, let's look at the next part of this problem. The next one is the limit of x to the power of 1 over x. So if we look at x to the power of 1 over x, as x approaches infinity, we get infinity to the power of 0. That's again one of those indeterminate forms. So we're going to have to take natural log. So we will take the limit as x goes to infinity of natural log of x to the power of 1 over x. So this is the form. And then we put 1 over x in front. So we get the limit as x goes to infinity, 1 over x, natural log of x, which is the same as natural log of x over x. And x approaches infinity. So what's the form of this one? Well, natural log of infinity, is infinity. And of course, the denominator is infinity. So this is infinity over infinity. So we can apply L'Hopital's rule to this one as well. So that means we have to differentiate the numerator, that gives us 1 over x, differentiate the denominator, that gives us 1, and x approaches infinity, so that becomes 0. But again, we took the natural log, so we have to take exponentiation here now. So the limit of x to the power of 1 over x is e to the power of 0. So the answer is in fact 1. And then one last example. Limit of root 2x squared plus 2x minus x. So this is the limit as x approaches infinity, root x squared plus 2x minus x. Okay, so again, what's the form of this? Well, the form is when x approaches infinity, the first one approaches infinity, the second one also approaches infinity. So we'll have to apply algebraic manipulations. So what works here is to multiply by the conjugate. So we're going to multiply both numerator and denominator by the conjugate of this, which is root x squared plus 2x plus x on top, and the same thing at the bottom. That would simplify the numerator, and it turns this difference, which was really the problem here, into a sum. Okay, so the numerator becomes x squared plus 2x and then minus x squared. And the denominator is root x squared plus 2x plus x. Now, the dominant term in the numerator is this term. In fact, those two terms cancel. The dominant terms in the denominator are these x's. So we're going to factor those dominant terms. So we're going to get the limit as x goes to infinity, 2x over, if we factor an x, we get root 1 plus 2 over x, and then plus 1. So we get the limit as x approaches infinity, 2 over root 1 plus 2 over x plus 1. Now 2 over x approaches 0. So this one approaches 0. So we get 2 over 1 plus 1, which is 1. So the answer to this limit is in fact 1. So as you saw, infinity minus infinity in the first example became 0. In this example, infinity minus infinity became 1. So infinity minus infinity is again one of those indeterminate forms, which means it could be basically anything. Indeterminate form means it doesn't really have a specific value. It could be anything. So here are all of the indeterminate forms that you will see in this course. The first one is 0 over 0. You can apply L'Hopital's rule. You might have to repeat L'Hopital's rule multiple times. Next one is infinity over infinity. Now it could be plus or minus infinity. Then you apply L'Hopital's rule for that one as well. Then we have 0 times infinity. This infinity could be positive or negative infinity. this infinity. Same for the exponent here as well. So if you have 0 times infinity, we would put one of them to the bottom, we turn it into 0 over 0 or infinity over infinity, and then we apply L'Hopital's rule. If we have 0 to the 0, we take natural log, and then we go to the product. We go to row number 3. If we have 1 to the infinity, we take natural log, and then we refer to row 3 as well. And if we have infinity to the 0, we again apply natural log, and then we refer to row number 3 because it turns into a product. If we have infinity minus infinity, then we'll have to do algebraic manipulations and then decide what to do. But most of the times in this class, at least, you'll end up with a L'Hopital's rule, but not always. Forms that are not indeterminate. So if you take 0 to the power of positive infinity, that's just 0, because 0 is basically like a very small number, because these are all on limits. So if you take a very small number, raise it to a very large number, it would just become 0. It is not an indeterminate form. If you take infinity divide by 0, then you would get infinity, because dividing by 0 means you're increasing the number. If you take 0 over infinity, then you get 0, because dividing by infinity makes the number even smaller. And that brings me to the end of this video. So I will see you in the next video.